So yesterday we talked about categorical displays as we're going through this data analysis section or unit here. And so categorical displays, we talked about bar graphs, side-by-side bar graphs, and pie charts. Kind of talked about the ins and outs of those. Those are really pretty basic in terms of we create them, and then as far as describing, it's mostly looking for the largest category, smallest category, and things like that. There's not a whole lot involved. With quantitative displays, we're going to have a lot more complex analysis that we can perform with it. And so we're going to talk kind of in chunks kind of throughout this next part of the unit here. So we'll talk about how to create the displays, we'll talk about how to describe the displays, what are the different measures we can utilize, and when to use each one. And so today we're just going to focus on creating some of the displays, so histograms, Stemplots, and Dotplots. So before we get into that, a couple of quick vocabulary terms. When we work with quantitative variables, it's important to understand there's two different types. There's a discrete variable, which is one where we can count or list all of the possible outcomes for that particular variable. So like a basketball player taking 10 free throws in a game. They could make 0, 1, 2, 3, and so on. We can actually list the different outcomes that could be occurring. Versus a continuous case, which would be dealing with anything that could happen, like anything that has an infinite number over a given interval. So it could take on any value within a given interval, like the number of amount of time spent studying the night before a test. So there's not like a specific, you can study 1 minute, 2 minutes, 3 minutes, and so on. You could study any increment of time over a given interval when preparing for that next test there. So that would be a continuous variable because we don't know what value you would take. It could be anything within that interval. And so just understanding the difference, these aren't going to play a major role quite yet. A lot of the things we're going to be talking about are the discrete cases, but this will be a more major topic kind of moving forward into some of the later topics that we have this semester. So just kind of keep that in the back of your mind for now. There's going to be a couple questions on the homework asking about the difference between discrete and continuous. So just understanding discrete means I can list it or count the number, the different values that go in. Continuous is it could be anything over a given interval. As far as the actual displays then, we have dot plots, which we've already talked about. We created one of these with our class activity that first week of school. And so just as a reminder, as we talked about that, during the activity, we're showing it on a dot plot. We show each value as a dot above its location on a number line. And so as we look at the steps here, just a couple of things to point out or highlight. When we draw the horizontal axis, we put the name of the quantitative variable underneath. So we need to make sure we label the number line with units attached, if appropriate or if available. When we scale the axis, we need to make sure we accommodate the smallest and largest values. And then the other thing is making sure we place tick marks at equal intervals until we exceed or equal that largest value. So just making sure, again, we're evenly spacing our increments. As far as the actual values on the number line, we do need to make sure that we have a place for every possible value. So I need to make sure that there's a spot. It doesn't have to be labeled on the number line, but there has to be a location where I can place every single dot somewhere on that number line. So again, we're going to have a set list of values that we can use, and we're going to make sure that we can plot each of the different dots on that number line. So for example, if we look at the number of goals scored by the 2012 U.S. women's soccer team, so in all the games they played that year, we have how many goals they scored. If I was going to create my dot plot, that first step would be to create the number line like we see here. So we go from 0 to 14. Now you can go a little bit below or a little bit above the minimum and maximum value if you would like to on a given number line, depending on kind of where you start and stop. But you can go straight from lowest to highest if you want, if that's easy enough, like they did here. And then the other thing you note, they did not place a tick mark for every possible value in our data set. So we marked all of the even numbers, but we did create spaces for those odd numbers to occur. So even though there's not a space labeled there, it's implied that this space would represent a 1, this would represent a 3, this would represent a 5, and so on. And so the other thing with that then, I could skip a number as I'm listing, so we're just kind of making sure things are spaced and nicely organized there. I could create a number line If I have decimals involved, where maybe my lowest value is 9.0, then I go 9.5, 10.0, 10.5, and so on. And what's going to happen is I have these decimal values, so I need to make sure that I have a space provided where I could go 9.0 if there was a value for that, but then I also have a space for 9.1, 9.2, 9.3, 9.4, and then 9.5, and then I create my graph based off of that, okay? So just making sure that when I create the number line, not every value has to be labeled, but there does have to be a space provided for every possible value so that we can create a dot above the appropriate location on the number line. And then outside of that, it's just a matter of then taking that information and then describing, which is a later topic for this week. Stem plots are going to be a little bit more involved. The dot plots are the easiest graphs to create. Stem plots are going to be a little bit more involved. And so when we look at a stem plot, there's going to be two parts to this that we want to be aware of. So we're going to separate into a stem. So that stem is going to be all of the digits minus the very last digit of each number. So whatever the numbers that we have are, we cut the very last digit off. Everything that remains is the stem. And then the leaf would be that last digit that we cut off. So those are going to be the two things that we're kind of interested in. So like for instance, if I had a data set, okay, we'll just make a little small one here. So something like this, if I'm talking stems and leaves, my stems would be all but the last digit. Oops. So stem, the 12, the 13, the 12, the 14, and the 16 would be all my stems. And then the leaves would be all of those last values that I'm cutting off from the stem. So I'm just taking whatever the last value is, cutting it off. That's going to be the leaf. Everything that remains is the stem. So when I make my stem plot, as we see the steps below here, I'm going to start by creating the stems, creating the leaves, and then I'm going to write the stems in a vertical column from smallest to largest. This is important here. So in my example from up above here, I would have my 12, I would have my 13, my 14. Now the other thing, making sure as we do this, we do not skip any stems. So this is a really important part right here. So do not skip any stems. So even though I have 12, 13, 14, 16 in my stems for my list, when I actually write the stems, I still need to account for the 15, even though there's nothing with it. And that's because I'm creating a number line. I'm just organizing it differently than we did with the dot plot. So I cannot skip any stems, even if there's not one available in the data set. I need to make sure I have that so that the gaps that are created can be identified when I go through my description and analysis. So make sure you have everything from start to finish, my lowest to largest value. I cannot skip numbers because I'm creating a continuous number line. When we get those, then we're going to create the vertical column next to it. And then all we're going to be doing is adding the leaves onto that. And so you can do this next piece in 2 steps where you write all the leaves and then recreate the stem plot with all the leaves in ascending order. Or you can go straight into putting everything in order right off the bat. So I could put the lowest stem first. So like the 124 and the 127 then in order. Then I got my 134, my 142, my 167, and I get my stem plot created from there. Once I have everything organized, then I'm going to create a key, and this is a really important part here. You always have to have a key that tells us how to read the numbers. So the reason that's important is this number here, if we highlight like this piece right here, that number could be the 124 like it is in our data set. It could be 12.4. It could be 1.24. So there's a lot of different possibilities for that number. And so we have to tell people exactly what that number is. So what is that number and what is the context of the problem? So as we look at an example here, We have the heart rates, so the resting pulse rates for 19 middle school students, and they're measuring that in beats per minute. And so we have the data set with the 19 values, and we look at the setup here. We have our stems, would be all but the last digit in each of these. And so once we've highlighted what those stems are, then we go ahead and organize them from smallest to largest. So from top to bottom, smallest to largest. Even if we skip a stem, like in this case, the 11 stem doesn't exist. There's nothing in the data set with an 11. So in that case, I still have to include it for the number line, but it's just gonna have a gap like we see here. As far as the next part then, once I have the stems organized, then I can start to add the leaves. So again, this step right here, you can do it like exactly like you see on here, where you create the stem plot and then you take all the leaves and reorganize them and create the final product here. Or you can go straight to that final product directly. Just make sure you stay organized as you're putting those leaves in, that you're not missing leaves or double counting leaves. So it's just a matter of just paying attention as you put it together. So once I get all that put together, I have my leaves in order. Now I have my distribution. And then the last thing I need to do is make sure that I provide that key. I need to make sure I tell people what those numbers mean. So in this case, the 8 and 2 represents a student whose resting pulse rate was 82 beats per minute. And so that's what we're doing when we're creating these stem plots. So they take a little bit longer. Got to be a little bit more diligent in how you put it all together, making sure we have the correct leaves, making sure we're putting them in order, and then just making sure we account for all the stems and then create from there. The other thing with stem plots then is there are times where all of our data might be bunched up within just a couple of stems. And a lot of times with our graphical displays, we want to try to have at least a couple different classes. We want to try to have about 5 to 10 classes so we get a real good look at what the overall shape of the distribution looks like. And so in the original problem from above, we had the stems like 12, 13, 14, and so on. What I could do with the split stems. So if I'm going to split stems, what I'm talking about is I'm taking the original stems, which were 120 to 129, 130 to 139, 140 to 149, and I can split those. So I can do 2 12s, 2 13s, 2 14s, and so on. And now instead of 120 to 129, this first stem would be 120 to 124. The next stem would be 124 to 129, and so on. So that I'm just breaking those classes up slightly so I get more stems to get a better look at the overall shape of the distribution. And when we talk about splitting stems, it's something you can do, you don't have to do. There's never a time where I would say you absolutely need to split or you absolutely should not split. It's just kind of a preference thing. You just got to think about the data, think about what it's going to look like and how you want to organize. The other thing then is that back-to-back stem plot. So this is the other one where basically it's a way of comparing, kind of like with our side-by-side bar graph from yesterday. And so we're going to compare two distributions directly by creating a stem plot in each direction. So like I would create my stem plot the regular way where I have my leaves on the outside here in ascending order, okay? And then what I'm going to do is if I have a second set of data, so a second group measured on the same variable, I can create another stem plot moving the other way. So I could have something like this where I'm having two sides to the stem plot, one side for one group, one side for the other. And so what that might look like, if we look at this data set, so they asked a group of students how many pairs of shoes they own. They separated the students into males and females, and they wanted to compare the numbers of shoes that the individual groups contained. So first, if you notice, we split the stems. So then instead of just doing a single stem for each class, we're doing 2 stems. The other thing I want to make note of here, when I have a situation where, like in this case, I have some single-digit numbers. When I do my stems and leaves, we're cutting the last digit off. Well, if I only have one digit to begin, then my stem would have to be a 0 placeholder in the tens place. And so that's where these zeros are coming from, is for those single-digit numbers. And so if I split the stems, my first group is 0 to 4, then 5 to 9, then 10 to 14, 14 to 19, or 15 to 19, and so on. So I split the stems up. I have all of my stems accounted for, even if some of them don't have, like in this case, these are gaps in the stems. It's okay to have gaps. We just have to make sure we have everything accounted for within that. And then the other thing, since it's two different groups of individuals, my stems need to accommodate the largest and smallest values. So I need to make sure those stems span the entire data set for both groups. And then like we talked about, we're going to break the stems off to one side for one group, so the males are going off to the right, females off to the left. And then the last piece is just making sure we create that key telling us the context and the way to read those numbers. Is it 49? Is it 4.9? And so we have to make sure we tell people what that's going to look like. Last thing then, histograms, which are probably the most common type of quantitative display. Stemplots and Dotplots are very nice because they actually account for every single value in the data set. And so we can see in the display itself what are the different values that we have. But because it accounts for every single value, they can be really difficult and really time consuming to make when we have larger data sets. And so that's where histograms might make things a little bit easier for us. So what a histogram does is it groups nearby values together and shows each interval as a bar. So it's kind of like a modified bar graph, where in the bar graph we had completely separate categories. So we spaced out the bars, we had gaps in between to show the different categories and then compare. This one's going to keep track of those bars on a continuous number line. And so what we're looking at down below is just a comparison between what a dot plot and a histogram would look like for the same set of data. So some things to point out here. When I look at my dot plot, we talked about the fact that there needs to be a space provided for each value in the data set. So what we're looking at is we have a 1.5, we have a space for 1.6, we have a space for 1.7, and so on. So I have the individual values for my data set built into the graph. Whereas in the histogram, this first class would span 1.5 to 1.75, just below. The next class would span 1.75 to 2.0, and so on. So what's going to happen here is I'm going to have all the 1.5s up to but not including 1.75 in this first group right here. The second group is going to have the 1.75 all the way up to but not including 2, and so on. So now we're just grouping the data a little bit differently. And so what we notice is, if I'm thinking about how this works, what's going to happen here is, as I'm looking at this bar that I create right here has all of the values. So we're looking at how many values are within the 1.5 to 1.75. That would be every one of these values right here. So three different classes in my dot plot creates one class in my histogram. So I got the 1.5s, the 1.6s, the 1.7s. And then when I go to the next one, so if I'm looking at this next class here, so the 1.75 to 2.0, that's my 1.8 and 1.9. I'm not going to include the 2.0, that's where the next class starts, but I'm taking all of those values and placing them into the next bar. And so all I'm doing is I'm keeping track of how many outcomes occur within that class. But the one thing we do lose is when I evaluate these bars here, I don't know what the individual values actually are. I just know that within the 1.5 to 1.75 range, we have about 17 values. Or in the 1.75 to 2, we have about 40 values. And so I don't know what the individual values are like I do in the dot plot, but I can create the histogram much easier by not having to account for every single value on the graph. So I can just create a bar for how many are there, and then I can work from there. In this case, again, just some things, and we're going to talk about it a little bit more in depth on the next slide here. So I have my label for my x-axis. Notice the x-axis does not need to start at 0. That's something I should have mentioned with both the dot plot and the stem plot. When we're making our number lines, we do not need to start at 0 for that x variable. The y-axis, though, does still need to start at 0 when we're creating these histograms. So my y-axis has to go from 0 to my maximum frequency or relative frequency, but my x-axis can start wherever I want. And then all I'm doing is creating the histogram based on the information. So real quick here, just a couple of things to point out on the steps. So we're going to choose equal widths. So choose equal width intervals that span the entire data. More often than not, I will give you that information. I'll tell you start at this point, use this interval or this width for the classes, only to make things a little more consistent so you can check the answer key a little bit easier, but also on like quizzes and tests, it'll make it easier for me to graph or grade if everybody's graph looks exactly the same. So we're gonna make sure we span the entire data set, but we have equal widths as we go from one class to the next to the next. We're gonna create a frequency table. So frequency table or relative frequency table with percentages. So just like we did with the bar graphs, we're gonna have my first class and how many individuals fell into that class, then the next class, how many fell into that, and so on. I'm gonna create that frequency table just to compile my data. We're gonna create the graph, so drawing and labeling the axes. Again, we talked about the horizontal axis is where the variable goes. It can start at any number I want to and go to any number I want to as long as I'm accommodating that lowest and largest value in my data set. My y-axis has to start at 0 and go up to the maximum frequency or the maximum percentage, depending on what type of graph I'm creating. When I scale them, again, just making sure we have the tick marks at even increments for the y, making sure we have even increments for the x, which should be defined by those classes that we create, so the 0 to 5 and so on. And then the last thing is just drawing the bars. How many individuals were in that first class, how many individuals were in the next class, and so on, and creating our bars much like we did in a bar graph. So as an example, so the table here represents or presents the data for the percent of residents from each state who were born outside the US. So they looked at each state and they looked at what percent of their residents were born in a different country. And so they counted up how many individuals fell into each of the different classes. So what they were talking about and what you would normally get it here is you'll get the data set. So it'll tell you that this state had 5.7% of foreign-born residents. This state had a 2.7%. This state had a 13.8%, and so on. So the first thing you would do is you would take those numbers and you would compile this frequency table like we see here. So I created classes that go from 0 to 5, 5 to 10, 10 to 15, and so on. And so what we looked at is from 0 to 5, there were 13 states that had 0 to just under 5% foreign-born residents. So that could be like 4.9, 4.99, 4.98. So anything up to 5%. And so there were 13 states that did that. And so if I look at my graph here from 0 to 5, I went up to 13 and I created my bar accordingly. And then as soon as I hit 5%, I go to my next class. And in that class from 5 to 10%, there were 20 individuals. So in my next class, 5 to 10, there are 20 values in there. And then I just continue making the bars from there. The other couple of things to note, making sure we have our labels. So percent of foreign-born residents for the variable that we measured. Notice the intervals match the start of each class that I created in my frequency table. So 0, 5, 10, 15, 20. And then I have to make sure I have the 30 there to complete my last bar, even though I don't actually have any 30% or more. And then as far as the y-axis, we're talking frequency in this case. We did the counts, and then we just did even increments from 0 up to my max of 20. So a lot of it's the same as what we did with the bar graphs. It's just the changes in the x-axis where we have a continuous range of values. The bars touch unless there happens to be a gap. Otherwise, we got the same basic premise. And then from here, we can kind of see what's the shape of the distribution, and we can start our analysis based off of that. So you're going to get some practice with those different types of graphs in the homework. So just being able to create, being able to label and scale the x and y axis appropriately, and so on. Last thing here, just a couple of cautions. Make sure you don't confuse histograms and bar graphs. I know I compared the two as we were describing them. Bar graphs, though, are when we have completely separate categories. We have spaces in between the bars to actually separate out the different categories. Histograms are keeping track in the same manner, as bar graphs, but it's a running total on that number line. So it's a continuous list of numbers, and it's a continuous interval that we're creating from the first value to the next, to the next, to the next. So each bar runs directly into the next one. The counts in the frequency tables, or the percents if they make a relative frequency table, is not the data. So just going back to this one here, when we look at this frequency table, the 13 is not a data point. There were 13 states that had percentages between 0 and 5%. So the actual data points would be like the 2.4%, the 7 or 3.5%, the 1.2% for each individual state. So the 13 has nothing to do with the data other than it's telling us how many states fell within a given class. So don't get those confused with the actual data, which are the percentages of foreign-born residents. And then making sure when we compare distributions, using percents instead of counts, especially when we have a different number of observations in play. So if one group has 500 individuals, the other group has 700 individuals, I can't compare counts directly. I need to convert to percentages so that we're on an equal playing field. And so then with that, you should be able to complete the homework today, which is a worksheet. You can get that in class or on Google Classroom. Just practicing building these different graphical displays before we start talking about how to interpret them.